In this example, we're looking at an application of exponential functions where you're given the exponential function. So here we have a radioactive material decays exponentially. It obeys the function a of t equals 25 times 4 to the power negative 0.058t. So t is time in years, and then the amount after time t is in grams. Questions. First, what's the original amount of the material? Original amount is always that coefficient out front here. So it's the number 25. So 25 grams. The base used to model the decay is the base of the exponential here, the number 4. And how much material will remain in 23 years. So let's plug that in. A of 23, that'll be 25 times 4 to the power negative 0.058 times 23. So this is just a matter of plugging it in. (25) times 4 to the power, don't forget to use parentheses, negative 0.058 times 23. So you get 3.93, it's big long decimal. And I guess the question is, how do you want to round this number to make sense in the context of the problem? So it's in terms of grams, so maybe it would make sense to have a tenth or a hundredth of a gram. So I'd say we should maybe round, it doesn't tell me, so maybe let's round to say 3 places. So if we look at this number, it's going to be 3.9336. I'm just going to write down the number right after the amount of places I need. And then, of course, look at the digit to the next of that place. And if it's 5 or more, round up. So I'd say it's approximately 3.934 grams. And how long will it take for there to be only this many grams of the material left? Also, we need to make sure we know what we're doing in all of these problems. So first, since this material is decaying, we should expect that if we started with 25 grams of the material, that after, say, 23 years, we're left with a little bit over 3 grams of the material, so it is decreasing. So this does give us a number we expect. So how long, we're going to solve for t. How long will it take for there to be only this many grams left? So let's go ahead and set our function equal to that many grams, and we'll try and solve for t. So the first thing we'll do is divide that coefficient. So we get 4 to the negative 0.058t equals 1.5625 divided by 25, which gives me 0.0625. Now I have to think if I can rewrite the two sides here so that they have a common base. So this is the number 4. I wonder if I could write this number with a base of 4 by using negative exponents. Like 4 to the power negative 1. What is that? 0.25. What's 4 to the power negative 2? That's 0.0625. That's exactly what I'm looking for, right? So now I can rewrite this. 4 to the negative 0.058t equals 4 to the power negative 2. And now you can set those exponents equal to each other. Divide both sides by negative 0.058. And then we should get an approximate time for t. So 2 over 0.058. So we get t is approximately 34 points. Let's maybe round to the nearest hundredths place. So if that's an 8, the next digit is a 2, so that'll keep it at an 8. 34.48 years. make sure that I'm using the right units. The original problem, t was in years, so I did do that correctly. So it would take this many years for it to decay to 1.5625 grams. Now, what's the half-life of the material? So that is where you take your equation and set it equal to half of the original amount. So half of 25, that would be 12.5. And then we'll solve for the amount of time that takes. And here's where we could have done that shortcut. 12.5 divided by 25 that's 1/2. So I set the equation without the coefficient equal to 1/2 to find the half-life. And now we have to rewrite, can I rewrite the number 1/2 and also the number 4 so that they have a common base? I can. 4 could be written as 2 squared. And 1/2 could be written as 2 to the power -1. So now let me just remember that when I'm raising a power to a power, I multiply those powers. So it'll give me -0.058 times 2. So 2 to the -0.116t equals 2 to the power -1. And now we can just set those exponents equal to each other. Divide both sides to get t equals 1 over 0.116, which is approximately 8 point, let's say round to 2 places, 8.62. And since we're solving for t, our units are years.